So we have Michael Hayden with the chemical clocks and the chemical tagging with GALAH.
All right, can you all see my screen?
Yes.
All right. So good morning, everyone. I'm Michael Hayden from the University of Sydney, and I'm going to talk to you about chemical clocks and chemical tagging with GALAH. So why do we want to do all this? Well, ages are kind of the holy grail for galactic archaeology. If you want to study the formation and evolution of the Milky Way through time, you really need something on that time axis. But it turns out it's actually really hard to measure ages for most stars you observe. And you can only actually get accurate ages for small portions of the HR diagram on the main sequence turnoff or subgiant branch, or if you have something like astroseismology from the Kepler or TESS missions. Now, the downside from Kepler and TESS is that you're only looking at specific regions of the galaxy or for very bright stars, so you're not really probing most of the stars that GALAH observes. And so I'm highlighting here why it's actually really hard to get ages for things. So I'm showing here a sequence of isochrones, and an isochrone is a line of constant age in this plot, so each line is the same age. And then the different lines are different ages. So you can see that we have like the young stars up here at 1 gigayears on this line, and the oldest population is at 13, and then there's some range in between. And so the main thing that pops out is on the main sequence here and on the giant branch up here. It doesn't matter if you're young or old, all the isochrones are just stacked right on top of each other, okay? So if you measure the stellar parameters for these stars, you don't have any hope of getting the age if they're on the main sequence or on the giant branch. And it's only in this special region here that I've highlighted by this yellow box where the isochrones are actually separated out, and you can say, oh, okay, this star lies here, it's next to a 1 gig-year-old isochrone, so it's a young star. So it's only for a very small subset of stars that you observe that you can actually get ages. And so this is where chemical tagging and chemical clocks might come to our rescue. And so what is chemical tagging? So the basic idea here is that stars contain the chemical imprint of the gas from which they formed, and that stars that are born together share the same abundances. So if you can measure enough different abundances, you can actually tag stars directly back to their birthplace. And so the idea here is that you're going to use galactic chemical evolution, the fact that the abundance patterns of the inner galaxy are different from the solar neighborhood or different from the outer galaxy, to act as your age tracers or your chemical clock. And so this plot here is the kind of something that underpins all of galactic archaeology, but really the critical for the results I'm going to show today. And so this is our periodic table from Chiaki Kobayashi. And the x-axis on all of these different elements here is time, where the Big Bang is on the left-hand side and then present day is on the right-hand side. And then the y-axis is the abundance of each element relative to the sun. And so the key thing to note here is that all the different elements are coming from all sorts of different production sites. And those production sites all have different time scales, right? So if you look at something like magnesium, you can see it's mostly coming from core collapse supernova, which happen instantly after a star formation event, while something like yttrium or barium has most of its contribution is coming from AGB stars, and those have a much longer ramp-up time. So if you can measure enough different abundances that are all being made from different production sites, you can actually trace the enrichment history of the galaxy through time, and also trace like a particular star to a particular place in the galaxy if you can measure enough of these abundances reliably. So getting ages from stars is not something that's new, or for ages from abundances for stars, sorry. So this is now, I'm showing alpha versus iron or magnesium. It's an alpha proxy. And you can see here that once you're magnesium enhanced, above magnesium about 0.1, you can almost just directly read off the age. So if you're magnesium enhanced between 0.1 and 0.4, you're a very old star, right? So 14 gig years old, but 10 gig years old, something in that range. But once you get down to young ages, something like 8 gig years and younger, you can see the magnesium is more or less constant. So magnesium is a great age indicator for old things, but it loses sensitivity for younger populations. So you need more than just magnesium if you want to try and age stars based on their abundances. So what about an S process? So a yttrium, I mentioned that before. What if you have yttrium? And you look at this plot and you say, oh, we're done. Everything's perfect. All you need is yttrium. It's a perfectly straight line. It's beautiful. Unfortunately, it's not that simple. So this paper from Neeson in 2015, obviously very small sample size with 15 stars, but critically, these are all solar twins. So these stars all have very similar metallicities to the sun and maybe don't span a huge range in parameter space, like something that GALAH would observe for all the stars in the galaxy. And so when you actually expand your parameter space and cover more of the galaxy in terms of metallicity, it all kind of breaks down. So now you see our yttrium to magnesium again on the y-axis and time on the x-axis again, and you can see it's basically a scatter plot. And so this looks pretty disappointing if you're trying to do chemical clocks, but actually, when you break it down, you can see the metal-rich things, stuff in red, do have a trend, and then metal-poor things, stuff in blue, have a different trend. but they actually do have some sort of slope here that might be applicable to doing chemical tagging or chemical clocks. So why might all these trends be different based on your metallicities? Well, if you think about it for a second, if you take stars that are 6 gigayears old, the stuff in red, the stuff that's very metal rich, that was likely born in the inner galaxy where star formation rates were higher compared to something that's in blue that's metal poor. And the metal poor stuff is probably tracing the enrichment history of the outer galaxy. So what we're actually probing here is different galactic environments for these different metallicity bins, where the metal rich things are probing the inner galaxy, metal poor things probing the outer galaxy. And so we're really seeing variations in birth radius. And so that's the key here, is that you're actually, the metallicity and age go together to make your birth radius, and then you're measuring a different yttrium to magnesium trend for different birth radii in the galaxy. But the take home is that you can't just fit one single line to things and hope that it'll magically work. You have to do something a little bit more sophisticated to actually do chemical tagging going forward. So this is something Sanjeev and I wanted to explore. And so we took the idea that the age and metallicity define a birth radius in the galaxy, and then we want to test if we know a particular place and time in the galaxy, like the very inner disk, and can we predict how the abundances are going to vary? Do you need any other information? So what we did is we adopted a simple model to predict abundances based on the birth radius, and then we compared those to what GALAH measured to see how much scatter there was about each age abundance relation in different locations in the galaxy. And so that's what's shown here in this plot. This plot might look a little bit scary, but it's actually not too bad, and it highlights why GALAH is so unique in its ability to do this. So the x-axis in each panel is age, and the y-axis is the actual abundance. And then each separate panel is a different abundance. So you can see that GALAH is measuring, about 30 abundances in total for GALAH DR3. And I'm going to highlight a few here. So this is our yttrium. So this is our S process element, this panel here. Similar barium is another S process here. And you can see that when you're yttrium enhanced, you're very young, and then as yttrium decreases, you get older and older. And the other thing that I'll highlight on this plot is that the different lines are different metallicities, or tracing different birth radii. So the metal-rich things are tracing the evolution of the inner galaxy, while those the metal poor are tracing the evolution of the outer galaxy. And you can see the global trends are quite similar. Now there is 0 points in the yttrium offsets, but we've corrected those out so that you can see how the trends compare to each other. I'll highlight a few others here. So these are our alpha elements down here. Again, you can see for young things, alpha isn't a great age indicator, but again, for old things, alpha is very useful. I'll also highlight one. So lithium, you can see, has catastrophically failed. If you want to use abundances as a chemical clock, lithium is not a good bet. And so lithium's a pretty special element and has special depletion and creation mechanisms that people like Jeffrey will talk about later. But you can see that some of the elements are very good, like yttrium and barium and alphas, and some, like lithium, aren't so good. So we actually quantify that here in this plot. So again, we're taking our birth radius, we're estimating an abundance based on fitting a relation to that, and then we're comparing that to what GALAH actually measured and determining the scatter. And so our measurement uncertainties in GALAH are about 0.05 dex for different abundances. And we're saying, all right, what's the difference between what we predict from the birth radius and what GALAH measured? And that's what's shown in the green triangles, like the intrinsic scatter and these different age abundance relations. And so if you want to do chemical clocks, low numbers are really good. So you can see that for most of the elements, what's that? 2 minutes? Okay. So you can see here that the green dots are all below our measurement uncertainty. So this is actually really good news for chemical tagging. And you can see, like for one, like lithium, it catastrophically failed. But for most elements, they do have age information. So GALAH is offering us a way forward. So we're turning this idea around. If age and metallicity define an abundance plane, the abundances and metallicity should define an age plane. So we're going to take these turn-off stars that we have good abundances for, good ages for, and we're going to feed it to machine learning algorithms. And so we're feeding it these age abundance relations for all these different elements and seeing if it can learn them and get chemical ages out. And so that's what I'm showing here, so that we're using XGBoost, which is a decision tree algorithm, and feeding it all these different abundances and ages to see if it can learn. And so the x-axis here is our age from isochrones, and the y-axis is our age from the abundances. And you can see we're actually recovering ages accurate to better than 1 gigayear for a lot of the stars. And so actually our age uncertainty from the isochrone matching itself is actually 1 gigayear. So we're essentially recovering our errors in our original age estimates. So this is great news. We're actually tagging stars directly to where they were born and getting an age out. So this allows you to actually apply ages for the whole GALAH data set. So you're not restricted to some small subset of the HR diagram. We'll skip that. So this is the last slide. What elements matter for chemical clocks? So this is what XGBoost has said is most important for getting an accurate age. And the top two are alpha elements. So that's magnesium and silicon. That makes sense from what I've already showed you, right? That if you're alpha enhanced, you can immediately say the star is old or young. The next one down on the list is yttrium to iron. So this is an S process element. Again, very critical for determining ages if you're younger. Then we have another alpha element in oxygen. And then the next one down is S process element barium. So basically the take home is if you have an alpha element and you have an S process element, that's almost all you need to get a reliable age indicator. You just can't fit a simple straight line to things. You need to do something a little more sophisticated. And so the machine learning algorithms were actually able to learn these relations. So I'll just leave you there on my summary.
Great. Okay, so well done. We have a question from Lisa on the Zoom chat. Do the models still predict that 1 million stars with ages and abundances will be needed to track back the full Milky Way history?
So I think the more stars you have, the better you can do. And particularly, the more the stars that GALAH observes, span a range of birth radius, range of parameters, and so you're not covering all areas of the galaxy as well as others. And so yes, having as many stars as you can just to make sure that you're covering like the inner disk and the outer disk well is really important. So the more stars you can get, the better. And it just depends exactly on what you're doing for how many stars you specifically need. Especially if you want to slice things in many dimensions, like the kinematics of the galaxy based on age. If you only have 10,000 stars, it's just not going to work. So yes, you need as many stars as you can to make sure both you cover the parameter space well, and that as you're slicing in more and more dimensions, that you have enough sample size that you're not dominated by noise.
Okay, so we have another question on the Slack channel. So from Katie, has the GALAH team looked into implementing multiple dimension reduction techniques to help separate stars with different chemical origins, such as PCA?
Yeah, so actually, there's one slide I didn't have time to show, but actually, so you can use something like PCA to determine which elements vary together. But this is actually a result from the paper that Sanjeev and I did, where you're actually seeing now how the age abundance slope varies based on the metal production site. So you can see on the right-hand side here, all the things in red, these are all your alpha elements and your rapid neutron capture elements. So things that are primarily produced from core collapse supernova. And you can see they all group together. And then on the left-hand side is all your S process elements. So these are all elements that are coming from AGB stars. Well, at the top, these are all things that are iron peak elements and don't really have an age abundance slope. So you're actually able, if you just measure the age abundance slope, it almost tells you where the element is produced, if it's coming from core collapse supernova or some other source. And so yes, you can use something like PCA to try and reduce the dimensions, but actually each element does have slightly different, like even for core collapse supernova, there might be metallicity dependent yields for different elements. And so using each element individually is actually helpful rather than trying to reduce your dimensions. Having more can be helpful. Stephanie, you muted yourself.
Sorry. Great. So we have another question from Piyush on the Slack channel. So latest fire simulations find that azimuthal metallicity variations dominated over radial variations 8 giga-year ago and beyond. Do you plan to consider azimuthal metallicity variation at some point?
So actually what's very interesting about our results is the fact that this works at all implies that they're actually, at least in the Milky Way, the azimuthal variations are small. Because that's essentially what that plot was showing, where we attempted to estimate the age abundance relation and then compared it to what GALAH measured. And so you can see that the scatter in between what we measured and what GALAH observed was less than 0.02 dex for almost all of the elements, which is smaller than our measurement errors in the actual abundances. And so if azimuthal variation was quite high in the past, like a birth radius didn't uniquely define an abundance pattern, you would see a much more scatter in those relations that we recovered than, and that's not what we saw, right? We saw the scatter was very small. So that means that the azimuthal variation, at least for the Milky Way in particular, was very little going back through most of its history.